2 more days of class, today and Thursday. We are last week's class. Today's class, lecture A, we're going to be doing more with the confidence intervals and prediction intervals like we did in lecture B last time, lecture number 25. And then in the second part, we're going to talk about the middle part of the spreadsheet output, ANOVA, which stands for Analysis of Variance. That is most useful for multiple regression, but here in simple linear regression with one explanatory variable, we still want to get an idea of what's in that output. Our final exam is 10 days from now. Today is December 8th, 2015. Your final exam, 10 days from now, Friday of next week, December 18th. If you're going to see Star Wars, you probably should go to the early one, because we got our final exam pretty early the next morning, 8 o'clock. Okay, the official start time, by the way, is 8:15, but I like to give you a little extra time. So I will be here by 8 if you want to get here by 8 to start, and you'll have till 10:15. You know, our regular in-class exams we've had typically leave an hour and 40 minutes, so that's 100 minutes. So for this one, you're going to get 135 minutes, which is 35% longer. Is the final exam 35% longer? I'm not quite sure. I don't quite remember. It is a little longer than the midterms. It's not twice as long. It's probably not 50% longer. Maybe about 30 or 35% longer is an accurate assessment. I have to look at it to double check. I'm not going to give you old final exam problems to look at, but I will, to compensate, give you information about the types of problems to expect. Okay, so I will tell you that ahead of time. The reason I don't give out old final exam problems is because I reuse a lot of them. Partially to save myself some work and partially to help me assess between classes. You know, did this class really do better than that class? To sort of decide, was this teaching strategy more effective than that teaching strategy? It's sort of a mini kind of non-ideal experiment. It's not really controlled, but that's an informal way for me to assess maybe some semesters where I was able to teach better than other semesters with different approaches. But again, I will tell you the types of problems to expect. And certainly you can look at exam 1 and exam 2 to help prep you. You can also look at exam 3 from past semesters where we had 3 midterm exams where you guys only had 2. Those will all be helpful to practice. You'll be able to use an entire sheet of paper instead of just a note card to write stuff on, but don't go overboard, don't write too much on it. It is cumulative, as always, chapters 1 through 10 basically. There were a few sections here and there that we skipped. I believe there was a 3rd section of chapter 7, for example, that we skipped. Just glance and see if that's right. Yeah, 7.3 or something we skipped. Sections that say optional in the book were things that we skipped. Was there anything else? I think it was maybe section 3.5, maybe. 3.4 about ethics. It's important, but we skipped it. 2.5. Well, we actually didn't quite skip 2.5 in the big scheme of things. We skipped it when we did chapter 2, though when we did chapter 9, we essentially did chapter 2.5. It's about categorical data and two-way tables. So basically we did that. Basically it looks like the main sections we skipped were 3.4 and 7.3. We did pretty much everything else. Again, you may use one whole sheet of paper front and back to write anything you want on it, but that's not studying, just writing stuff on that, and you don't want to make it too full. You want to practice the old problems and newer problems that are again from old exam 3s, as well as problems I tell you to study, as well as some more I'll assign from the book that you won't have to hand in next week, but you can use to prep. You want to practice those before you make your piece of paper, and it's just, there is your security blanket again. Calculator, as usual, will be needed for the final exam. We've got 2 more quizzes today and Thursday. No calculators for those. Calculator will be needed for the exam, though. Make sure you get a good night's sleep and have a good breakfast also. Okay, I know it's early in the morning. Get some protein, eggs or something like that, sausage, before you come to the test. That's good. A little bit of carbs is okay too, just don't go overboard on the carbs. Don't eat a bunch of Lucky Charms before you come, okay? Probably not a good idea. All right, that'll give you the energy to see you through. You may bring a snack to the final exam if you want, though I've got two conditions. It can't be noisy, no chips, and it can't be smelly, no fish. Or onions or something like that.
I was going to bring some salmon in.
Salmon? You like that for a snack? All right, not noisy, not smelly. If you bring some pop, heaven forbid, open it before you start. You can bring some coffee, that'd be better. Don't cram, start studying today. You got the old exams, you got the old exams on Moodle as well. Don't cram, start studying today. Maybe about a half an hour each day for the next week or so, and then leading up to the last 3 days, you can up it to an hour or an hour and a half a day. Okay, although maybe some days you want to practice, do an hour to practice old exams, that kind of thing. Don't cram, all right? Remember those study tips that we talked about earlier in the semester. All right, plan for today. To start with here, we're going to look at those, the output that's in the book from the Minitab and review that. Then we will look at those formulas for the confidence intervals and the prediction intervals, standard errors especially, which you do need to know for the quiz. You need to understand the meaning of them as well for the quiz. Okay, then the second half of class, lecture B, we're mostly going to be focused on the spreadsheet and your last electronic assignment. Let me shut this down actually, so that it was difficult to see for the last lecture on the videotape. Those pictures that I put up on the screen. So you're going to want to zoom in with the camera on these things. Okay, so same example as last time. It's on page 552 if you want to look there in the book, if you can see it better there. That's about as sharp as I can get it there. Okay, so it's the book's example situation, this locus of control, LOC, and stress level for workers, accountants, okay? Again, high LOC meant you feel like you don't have much control of your life. You don't have much control, even though it's a high LOC, it's a little counterintuitive. And lower LOC meant you feel like you've got a lot of control over your life. And then stress level on some scale is Y. LOC is X, explanatory. Stress level is Y, response. And we're looking at this output. We're interested in understanding what happens for the accountants whose LOC is 16. That's the top here. They do explicitly say that's X star. However, you should realize that even if they didn't explicitly say it, that you should take that to be X star. X star is just whatever value of X you happen to be thinking about. We are going to think about people whose LOC is 16, so that should be the value of X star. Okay? It's just a special number. It's the special number we happen to be thinking about. If you had the equation of the regression line, you could figure out the number that goes with fit by plugging X star into the equation of the regression line. That is Y hat. When you plug in X star, in this case equals 16, into the regression line equation. We don't have it here. I think it might be somewhere else in the book. But here, in this output, we don't have it. But that is the best guess for the stress level of somebody with an LOC of 16. That's Y hat. This thing that says standard deviation of fit, that is SE mu hat, that thing that the book labels SE mu hat. Again, let me write it on the board. We've got the formulas for these intervals. You got the confidence interval to estimate the mean of the y's when x equals x star. Estimating the mean of the y's when x equals x star. The formula is y hat, that's your point estimate that you get from the regression line, plugging in x equals x star, plus or minus the margin of error. The margin of error is the product of a t-star value and a standard error. The standard error, in this case, labeled SE sub mu hat, which is a little strange. We hardly ever put hats above parameter things here, but we are doing that here. That's the symbolism that we use. That's the confidence interval, and the SE mu hat, that standard error is what's labeled standard deviation of fit. That's SE mu hat in Minitab's output. Then there's these prediction intervals, whose goal is to estimate an individual value of y, the next observation, when x equals x star. The formula is pretty similar. You still find y hat from the regression line, plus or minus a margin of error. That's still a t star times the standard error, but the standard error is different. It's labeled SE sub y hat. For the quiz and for homework and the test, you should know the purposes of these things. First of all, the purpose of this one is to estimate the mean of the y's when you're given a certain x. You're looking at a stacked data points above that value of x. Looking at their second coordinates, their y coordinates. What's the mean of those numbers? Not the actual numbers, but the expected mean based on doing inference. We've got sample data. We're wondering what the population mean is, not the actual mean of the second coordinates of the data points. The mean of the second coordinates in the population data is what you're after. So you want to estimate a mean. This is to estimate the next observation when x equals x star. You've done a sample. You're about to observe one more person whose x, LOC in this case, is x star, say 16. This interval is supposed to give you a 95% interval that you're 95% confident that it captures the next value of y. You can still use the word confidence with it, even though it's called a prediction interval. We still put a level of confidence of 90% and 95% and 99% with it. You can still say I've got that level of confidence, but we call it a prediction interval because we're using it to predict the next value of y. Confidence intervals are used to estimate parameters, a mu in this case. Prediction intervals are typically meant to estimate the next observed value. These are bigger than these are, and you can see it on the output. Look back up at the output again. Again, this number is SE mu hat. They're not giving us SE y hat here, though maybe we can figure it out. Do some problem solving. We will try to figure it out. 95% confidence interval, there it is. 95% prediction interval, there it is. You can see again the prediction interval is bigger than the confidence interval. That will always happen in this context. You can do some problem solving. You can figure out other quantities based on this output. For example, you can figure out the margin of error like I did here. I'm focused on the confidence interval at the moment. The confidence interval is going to be centered on y hat, 2.894. The margin of error, therefore, is the distance between, say, the right endpoint and 2.894. Let's go ahead and figure that out here. 3.0374 minus 2.894. If I can do that in my head, probably going to get myself into trouble here. 148, is that right? Somebody check me on that. No, that's not right. Somebody do that. Okay, I'll do it. 0.1434? I don't know where I got the 8. What I was thinking there. 0.1434. That's the margin of error here. we should be able to estimate that actually also with t star times the standard error for mu hat. The standard error for mu hat being 0.0722, or alternatively, if we plug in that standard error value, we could solve for t star. Actually, t star is not going to be exactly from the table in this problem because the degrees of freedom was 98, and that doesn't come out in the table. Let's solve for t star instead. The standard error for mu hat is 0.0722. So if I set these equal, I should be able to solve for what t star was. T star should be 0.1434 divided by 0.0722. I gotta go between calculator and transparency here. Let me just double check the subtraction. 3.0374 minus 2.894. Yeah, that's the 0.1434. Divide that by 0.0722, 1.986. That should be the value of t star. Is that in the table? Could we have gotten that from the table? The answer is no, not exactly. Again, the sample size here was 100, n was 100. So technically, n minus 2 is 98, but in our table, there's no 98 degree of freedom one. The closest one is 100 degrees of freedom. You should look there with me here. Everybody should be looking at their book. For 95% and 100 degrees of freedom, t star is 1.984, not too far from 1.986. Remember I said you often want to play conservative with degrees of freedom, which means round down. So actually, even though 98 is closer to 100, if we were using this table to find t star to begin with, we'd probably go ahead and round down to 90 degrees of freedom, which is also in the table. It gives you a less accurate t star, actually 80, excuse me, 80 degrees of freedom. 90 is not in there. It gives you a less accurate t star of 1.990. But it is a bigger t star, which leads to bigger margins of error, which is playing it conservative instead of risky with your confidence intervals. Anyway, the upshot is you should be able to do it either way. And in this case, you should be able to solve for t star like we just did here. And that, in turn, can allow you to figure out other kinds of intervals based on other kinds of confidence levels. Instead of 95%, we could do 99%, for example. Actually, we could do that without solving for t star, because this is the t star for 95%. You should be able to figure out a 99% interval. Go ahead and use, say, 80 degrees of freedom. Look at the back of the book again. 80 degrees of freedom, 99% confidence. We're using 80 degrees of freedom to play conservative. I see a t star of 2.639, right about there. Future people, you may not be using this book, and you might have a different table. 2.639 is the t star I see with 80 degrees of freedom for 99% confidence. So I could plug that in for t star and multiply it times the standard error of 0.0722 to find the new margin of error for a different confidence interval to estimate the mean. I could estimate a 99% one instead of a 95% one. Here I'm told what the prediction interval is. Is there a way I could solve for that instead of just being told what it is? Well, again, I do know t star. That's probably helpful. Can I figure out SEY hat? What are the formulas for SE mu hat and SEY hat? These are things you should know for the quiz today. I'll write them on the board. SE mu hat, kind of a complicated looking thing, is the standard error, S, not a standard deviation, although it's an estimate for a standard deviation. It's not a standard deviation of x or y. It's an estimate for the standard deviation of the epsilons in the regression model, which were random variables that were normal and had a mean of 0 and a standard deviation of sigma. That's the regression standard error. You've got to get all these things in your mind here. The formula continues as a square root of 1 over the sample size plus another ratio. The top of the other ratio is the value of x star you're thinking about minus x bar squared divided by what's really SSXX, this summation here. That's really the same as SSXX. That's SE mu hat. What about SE y hat? The formula looks practically the same. The only difference is there's a plus 1 in the square root as well. Which does make SEY hat bigger, and sometimes significantly bigger, which you would think wouldn't happen if you're just adding a 1. How could it be significantly bigger? The reason is because oftentimes what's under the square root here is a pretty small number, pretty close to 0. When you square root it, it's going to get a little bigger, but still will be close to 0. On the other hand, when you add 1 to it, it's going to be bigger than 1. A number barely bigger than 1, for example, 1.1, could be many times bigger than a number close to 0, like 0.1. 1.1 is 11 times bigger, multiplicatively speaking. It's 1 unit bigger, additively speaking, but it's 11 times bigger than 0.1. So even though you're just putting a point plus 1 in there, this number can be significantly bigger than that one. So what again are we doing here? We're trying to see if we can figure out the prediction interval if we were not given it. We've just figured out the margin of error for the confidence interval. That's the 2.89, the 0.1434. That's this thing times t star. We also figured out t star. We could therefore solve for that thing, and I'm realizing we're still not going to quite be able to do it, though, because we don't know s. Okay? So I have to tell you s if we were going to be able to figure this out. Are we given s anywhere here? Not in this output. Let me glance quickly through the book and see if I can find s in another output here for the LOC problem. Yeah, S, I do see it on page 534. S for this problem, the standard error, turns out to be, in the output on page 534, the standard error is 0.451277, I'll round it. 0.451277. Okay, so I can plug that in here, and that can allow me to solve for the square root. How? Let's do it. Okay, so again, what do I know? I know m is 0.1434 for the CI. That's the margin of error for the confidence interval. I know t star is 1.986. I know S, 0.451277. I know that the margin of error is also t star times the standard error, which can be written as S times that square root. Therefore, what I can do is I can plug in all the numbers except for the square root. And I can solve for the square root. I can divide both sides by t star and s. If I do that, I get 0.1434 divided by the product of these two numbers, 1.986 times 0.451277, and set it equal to that square root. go ahead and see what that is. Okay, what I'm trying to emphasize here is it's really problem solving. Okay, you're going to have some problems on this next assignment as well as some ones that I'll assign to prep you for the final. You want to turn them in. I'll give you a key for them. I'm trying to emphasize problem solving, algebra, really, by doing this. You can find things even if you're not given them, oftentimes. So in this case, what is this fraction? 0.1434 divided by the product, use parentheses here, of 1.986 and 0.451277. That's what the square root equals. Approximately 0.16. Close enough that I'll go ahead and round it to 0.16 there. I'll keep more decimal places of accuracy here on the screen. That's what this square root equals. Can I use that to figure out the other square root? Yes, I can, because if I square both sides now, this thing without the square root, inside the square root, that's going to end up equaling approximately the square root of 0.16, which is, oops, 0.16 squared, excuse me, which is about 0.0256. That's a 0.16 squared is about 0.0256. And now if I add 1 to that, that's going to give me what's under the square root here. Add 1 to that number, because that's the only place those formulas differ, is the plus 1 under the square root with the second one. Add 1 to that number, get this, take the square root of that number, get that, that's what the square root in the second formula equals. Standard error for y hat. I'm after the prediction interval here. Multiply that times s. S is 0.451277. Multiply that by t star, 1.986. And that is your margin of error for the prediction interval, if I've done everything right. Here we go, a moment of truth. Did I do everything right? Go back to the transparency. Moment of truth. Oh, I forgot what my answer was. It was about 0.9076. If I did it right, the right endpoint here should be the fit 2.894. That's the y hat, plus the margin of error I just got on my calculator, and I showed it to you, 0.9076. Is that true? Probably not exactly true, but is it close? 2.894 added to that. I get 2.6. Uh-oh, I'm not close. Ah. Oh no, wait a minute. I multiplied instead of added. That's why. 0.9076 plus 2.894. Yay, I'm close. 3.8016. Almost had a heart attack there. I multiplied by accident instead of adding. It's close. I didn't expect it to be exactly right because of some rounding. So the big point, okay? 10 minutes of tricky algebra that you probably don't want to watch again here if you were falling asleep. Problem solving. You can solve for some of these things even if you were not given them. If you were not given the prediction interval, you could solve for it. And once again, you could also solve for one with a different level of confidence, like 99%. Use a different t star. You can do algebra to solve for these. Don't be afraid to try. Sometimes you just got to try things. I think with math, sometimes people, they feel like they're going to make a mistake, so they don't try. You got to try things with algebra. See if it works. See if it makes sense. If it doesn't make sense, then try to redo it. Work with others, okay? These are all things that you can do and should be able to do. That took longer than I wanted. Any last minute comments before the quiz? Well, again, you should know the formulas for the quiz. I will erase them now. You should know that typically prediction intervals are bigger than confidence intervals for this purpose here. You can graph these things for various values of x, different x stars really, and you get graphs like this. That's a confidence interval to estimate the mean. You can see the margins of error are fairly small, and they're smallest close to x bar. If x star is close to x bar, that's when these differences are smallest, both here and here, making these standard errors smaller for when x star is close to x bar, making the margins of error smaller. So in these graphs, they get skinnier closer to x bar than when they're further away. Though the difference is definitely more pronounced for the confidence intervals than it is for the prediction intervals. You can barely tell there. Those are not straight here. They look almost straight here and here, but they're not. This is a straight line. That's a regression line, but these are not quite straight here and here. Those are the bounds, lower and upper, for the prediction intervals. All right, put things away for the quiz.